take a moment to read the question prompt and identify all the variables that were given. In this case, we have a projectile launcher that is on the edge of a table, and it's going to fire its projectile horizontally onto the floor below. We're given information about the ball as it's launched, where it is, and where the ball lands. And we want to find the launcher's muzzle velocity, how fast the ball is going when it leaves the muzzle of the projectile launcher. So the first thing we're going to do, the first thing we always do, is to draw a picture. So the first thing, I have a projectile launcher, and that projectile launcher is on the edge of a table. Our projectile launcher is firing horizontally, so it's going to fire a projectile out, and we know it's going to curve down and land on the floor. We're told that the launcher has a height of 1.25 meters above the ground level. And that the projectile lands 2.77 meters away. And so we want to find the launcher's muzzle velocity. So in this situation, we can see that this is projectile motion. The projectile is flying through the air here. It's not touching anything. Nothing's interacting with it. So the only thing influencing its motion is gravity, and that's our definition of projectile motion. An object flying through the air, nothing touching it, only gravity acting on it. So that's the second step. If we're trying to plan a solution, figure out how we're going to find the muzzle's velocity, we see that this is projectile motion, and we're going to solve this as a projectile motion problem. Step 3 is to actually execute the plan. When we're talking about projectile motion, remember that we have motion in 2 dimensions. We have vertical and horizontal motion, and so we'll split these two up separately. We'll consider horizontal and vertical motions separately. In the x direction, there's no acceleration at all. The acceleration is only due to gravity and is only in the y direction. And so our motion in the x direction is uniform motion. So we only have 3 variables. There's really only one equation for us to use, which is distance is speed times time. In the y direction, we have an acceleration. This is our free fall acceleration due to the influence of gravity acting on the ball as it flies through the air. And so that's going to be a constant acceleration equation problem for us. So we can start looking at what we've been given. We're told that the object is in projectile motion. The acceleration is only through the air, and so we're always given the value. We can assume the value of g. Make sure that you're using the correct unit system if you have metric or the American system. We're also told that as the projectile travels from the launcher to its landing site, it moves the height of the launcher downwards as it goes from the tabletop down to the ground, and then it moves along the ground. So the projectile launcher is 1.25 meters up in the air. The projectile's up here and it moves downwards. And so that is motion in the y direction. That's our y displacement. And it's moving downwards, so that should be a negative value. At the same time, the projectile is moving horizontally along the ground as it moves from here to here. And so this horizontal component of motion would be the delta x, the displacement in the x direction. Now we've accounted for all the numbers that we've been given, the height here and the distance. We have accounted for acceleration, which is not given explicitly, but is implied because it's a projectile motion problem. And we want to find the launcher's muzzle velocity. The muzzle velocity is the velocity of the object as it's launched. So this would be the initial velocity. We're not told anything about it specifically, numerically, but looking at our values here, we see that we don't have enough numbers here to solve this equation. We don't have enough numbers there to solve that equation. So we have to think critically a little bit about what we're looking for. We want to find the muzzle velocity. We want to find how fast the projectile is leaving that launcher. And we're not told anything about how fast it's moving, except we're told that it's being fired horizontally onto the floor. So this projectile launcher is going to have some initial velocity vi, which just depends on the internal mechanics, how fast it's able to launch that ball. But vi, all of this velocity, is being launched horizontally. So if we wanted to write out the initial velocity vector, it's going to be some value, whatever the unknown value is, but that's purely horizontal. It's going to be purely in the I hat direction. If we're launching the projectile purely horizontally, then we're launching that projectile not at all in the y direction, or 0 in the y direction. So while we don't know the initial velocity, we do know the initial velocity is only in the x direction, and that's going to be the value that we're looking for here, because the initial velocity is purely in the x direction. In the y direction, the initial velocity is 0. And so even though we're not given that explicitly, we can think critically a little bit about it and say that a horizontal launch would give us 0 vertical motion. And so you can see here, we have our 3 variables. So we can calculate all the things we want to know here. We're not actually interested in the y direction. We want to know the velocity of the launcher, and the launcher is being launched horizontally in the x direction. But remember, most projectile motion problems work on the fact that the motion in the 2 directions is independent, but simultaneously. So we have the 2 times in the x and y direction. The time that the projectile is moving from here to here, it's moving vertically in that time, it's moving horizontally in that time, but it's the same time, because really the projectile starts here and it ends there with 1 time displacement. So if we want to relate the times, that means that we need to find the time in the y direction, and we can come over here and plug it into the x direction. In the y direction, we said we have constant acceleration, and so we're going to use the constant acceleration equation that will help us find time. Start out by writing out the equation, and then in the next step, plug in the actual numbers that we're going to use. We see here that the 0 for the initial velocity is going to cancel out one of the values of time. So there's only 1 time left. It's time as a t squared, so I'm going to solve for t squared first. I found t squared, and then I can square root that to find t. Since this is a time, I don't need to worry about the plus or minus because time is always positive. Notice how I'm using a lot of extra decimal places so that I'm not introducing rounding errors in my calculation. And also, I'm not even going to use this value. I'm just going to leave it in my calculator, and I'm going to let the calculator deal with it for me. But I found the time here. This is the time in the y direction. But we said that that's also the time in the x direction because the motion in the 2 directions is independent but simultaneous of one another. So now we have 2 variables in the x direction. We're trying to find the velocity in the x direction because the velocity in the x direction is the only velocity that we have for our launcher at the very beginning. And so we'll be able to solve for that as well. Start by writing out your equation, then plug in the known values, and solve for the unknown variable Vx. This is a velocity, so it should be measured in meters per second. We use standard units all along, so we should get standard units here. We notice that we have 3 sig figs and 3 sig figs in our given value, so we're going to round this to 3 sig figs as well. And our final answer is going to be that the initial velocity was 5.49 meters per second. This is the initial horizontal velocity of the launcher, and again, since the launcher is being launched horizontally, that must be the muzzle velocity of the launcher as well.